for working at Goddard. You could go as a civil servant, and so then you would look for jobs posted on usajobs.gov, or as a contract employee. So, and those aren't posted one exact place either, unfortunately. So there is not one website to search for those. It's kind of just looking for like GIS and NASA jobs and Googling it, basically. Like it's a little more difficult. There's also like the Pathways intern program. So if you were a graduate student or if you were a university student and interested in going that avenue as well. So that one's sort of you intern to then work as a civil servant at Goddard as well. So there's that avenue. And then we do have some postdoc positions as well. So there's lots of different ways. All right. Now I will go ahead and share my screen. Okay, did the sound work? Perfect. All right. Well, good. Well, we are, I guess, ready to get started when you guys are ready.
Are we good to start?
Yeah, absolutely. Just a quick welcome really quick to everybody we have here. First of all, thank you so much for being here. We really appreciate your time. This is the APUS chapter of wSTEM and AWIS, and we also have people from AIAA and SEDS members that were welcome to our virtual field trip too. Again, we just wanted to say thank you for being here, and you can take it from here.
Thank you.
Great, thank you very much. And so, yeah, so my name is Amanda, and my co-host is Mr. DJ, or DJ. We'll talk to younger groups, so I was like, Mr. DJ. So DJ is my co-host. So we both work for NASA Goddard Space Flight Center in Greenbelt, Maryland, so right outside of DC. And specifically, we work for the Visitor Center location. And so today we're going to go over a lot of what we do here at Goddard. So I'm going to give you an overview of our work, and then we're going to talk about some of the missions within each of the different areas that we focus on. So here at Goddard, we highlight the sciences, we look at the sciences. So particularly today, we're going to look at some of the missions within earth science, planetary science, heliophysics, and astrophysics. And I wish we could talk about every single mission that we're working on, but that would take hours. And so we're going to kind of give you a highlight of some of the things that are going on here at Goddard. And throughout the presentation, I am going to turn my camera off because my computer gets kind of upset when I have my video at the same time as running a PowerPoint. So just so you're not like, why is she turning it off? That's why. But we'll turn it back on. And if you guys have any questions throughout as we're going, if you want to type those into the chat, we can try to grab them as we go. And then, we can definitely have time for questions at the end. So yes, thank you for sharing the link for the Pathways program as well. Perfect. All right. So to start with, I'm going to play this introductory video for you guys, because you can hear about Goddard through the voice of our scientists and engineers here.
At NASA Goddard, we build space telescopes.
To explore the evolution of galaxies, stars, and planets that make up our universe.
We discover planets around other stars and investigate whether they could support life and what that life might look like.
We imagine, then engineer far-out missions to answer questions about how galaxies and planets formed and evolved over time.
At NASA Goddard, we study the sun's dynamic behavior and the space weather that it generates so we can protect astronauts and satellites in space as well as our technology on the ground.
At NASA Goddard, we use the data from a constellation of satellites to generate global maps of rain and snow pummeling the Earth.
To monitor how greenhouse gases move through the atmosphere.
And to model all of the Earth systems to create a dynamic portrait of our planet.
We launch small rockets carrying university-developed experiments into space.
And provide low-cost space platforms for testing new instrument concepts and engineering techniques.
At NASA Goddard, we ensure every craft is space ready.
We blast noise and shake instruments to simulate stresses at launch.
We expose them to the unforgiving vacuum of space and to the powerful magnetic fields.
At NASA Goddard, we develop and maintain communication links between Earth and spacecrafts in orbit.
We evaluate and improve system software to reduce risk in our missions, large and small.
Innovation and science never sleep.
And new discoveries never get old.
At NASA Goddard.
All right, yeah, so that video gives you a great overview of a lot of the things that we're working on here. And they did show some clips of some of our other locations as well. So Goddard is very lucky in that we comprise more than one specific location. So we have 4 additional facilities. So we also have one in Wallops Island, Virginia, where we can launch. And we have White Sands, New Mexico, New York City, and we do software testing in West Virginia. So we're very unique in that as a center, as a Goddard Space Flight Center, we can do an image from start to finish. So we can imagine it, engineer it, create, test, and then launch it off of the coast. And then, so each one of these red dots represents an official NASA location around the country. And I did want to point out, I forgot to mention as well, so we do have just general internships that start at 16 years old. So I believe you guys are above 16, but so they are for students all the way through grad school as well. So if you're interested in applying for those, that's intern.nasa.gov. And so those are a great opportunity to sort of get started with NASA and see what interests you, to start to make connections and see what centers, fit with what your interests are. All right, so this is our center here. This is Goddard Space Flight Center in Greenbelt, Maryland, our main campus. So right here in the middle is our integration and testing facilities. And this is where we do all of our building and our testing for the spacecraft and the satellites that we are creating and making. And so inside, let me point out. So this big building here is our clean room specifically. And then this big wall here is the filters that you see right over here on the left side. So I clicked too many things, sorry. So these are the filters on the outside of that building. So this is inside the clean room. So our clean room is amazing. It's beautiful. DJ's been in there 4 times. I have not yet, so I'm very jealous, but I like to point it out before he does so that I'm not as jealous when I say it. So our clean room is fantastic. It's one of the largest ones in the world. It's 8 stories tall. We filter and cycle our air through here 42 times every hour, and our filters are able to grab something that's 300 times smaller than a human hair. So they're very efficient, very effective filters. It's really important that we clean the air so that we make sure nothing from us ends up onto our spacecraft or our satellite before we send it out into space. Because we can't clean it once it's out in space, particularly if something ends up on a lens, then there's nothing we can really do about it once it's orbiting around. So it's very important to keep that clean space. And then these images here show you the inside of our testing facilities that we have at Goddard, and you saw them in the video as well, but the one on the right in the red frame is our acoustics test chamber. So that is a 3-story tall speaker. So we're testing for 2 different aspects. First, we're testing to make sure that it can survive in the environment of space. So we have our space environment simulator on the left, and then on the right 2 images show you that we're testing to make sure it can survive stress of launch as well. So on the right is our acoustics test chamber. It's a 3 stories tall speaker, and we put our satellites in there and we seal it all up. We get all the humans away as far as we can, and then we blast the sound of a rocket launch at it to make sure that the vibrations from the sound don't cause any problems or damage to the satellite, because there's nothing we can't really do anything about it once it's up in space. So we need to make sure that the ride into space doesn't cause a problem. The middle image with the white frame is our vibration chamber. And so we mount the satellite to that circle, the metal circle on the base there. Sorry, I don't know why I don't just point. So we mount a metal plate with our satellite mounted onto it right here, onto our vibration chamber, and then we shake it like crazy. So it's very efficient. We shake it, it's like 3,000 times per second. So it's incredibly fast, incredibly powerful, because again, we want to make sure it can survive that launch into space on the ride in the rocket. And then we're checking to make sure it can survive in the environment of space. So around our Earth, we have our atmosphere that gives us our air and air pressure and all those great things that make Earth unique. So we need to make sure the satellites can function outside of that. So in this thermal vacuum chamber, we are able to take the top off, we slide it over, we lower our satellites inside. We close the top, we seal it up, and then these cylinders around the outside pump out all of the air, and it creates the vacuum of space inside of this chamber. So we can test to make sure that it will work in that vacuum. Then we're able to heat it up to a couple hundred degrees Fahrenheit for several weeks at a time to make sure that it can survive the extreme heat of space. And then we cool it down to maybe -300, -400 degrees Fahrenheit for another several weeks at a time to make sure it can survive the extreme cold that it may experience in space as well. All right, so now we're going to talk about a few of our missions within each of these science areas. And the first one we're going to start with is our Earth science missions. So DJ, can you tell us about our fleet of satellites around the Earth?
Oh, definitely. So NASA's Goddard Space Flight Center's Earth Science Division is the largest collection of Earth scientists on the planet. NASA studies all aspects of from the vantage point of space, as well as studies that involve aircraft, ships, and scientists on the ground all over the world. The Earth observation system is made of 23 satellites that have orbited or continued to orbit the Earth since the program began. The first of these satellites was launched on December 18th, 1999. It's called Terra. So the next 10 years, NASA is going to be building 5 new Earth science missions. The latest is Sentinel-6, which was launched November 21st, 2021. It's a 5.5-year mission to collect data on global sea level and how our oceans are rising in response to climate change. So this spacecraft is going to be able to measure sea level height to within about an inch. The mission also collect precise data for atmospheric temperature and humidity that will help improve weather forecasts and climate models. So one of the nice things that this Sentinel-6 has recently done is it was able to spot a methane leak in an underground pipeline in Russia. This was like June 4th, 2021. And methane is a major component of natural gas, and at the same time, it's 8 times more warming power than carbon dioxide. So it has spotted numerous methane leaks, and not just in pipelines, but also in landfills. So using that data, that we're able to figure out how to prevent these methane leaks from happening. So the next one I'm going to look is the GPM satellite, which you see on the left. So the GPM mission uses 9 international satellites provided by the United States, Japan, France, India, and Europe. The core of the constellation is the GPM satellite, which is what you see in front, which was launched on February 27, 2014. The GPM constellation provides a global map of rain and snow falling every 30 minutes. The satellite will scan the skies between the Arctic and Antarctic Circle. The GPM microwave imager, which you see rotating in the top, operates like an X-ray. It can tell the difference between water, snow, and ice. Each object, such as rain, snow, and Earth surfaces, emits or scatters energy based on the object's temperature and physical properties. Then there's a dual frequency precipitation radar, which you see underneath the box-like structure. It's like a CAT scan. It can provide information how many raindrops of different sizes, including snowflakes, are in the cloud layers and how they are spread throughout the storm system.
So this is a specific example of some of the observations from GPM. So this video of GPM observations of Hurricane Arthur from July of 2014, it really shows what GPM can do. So if you, so its radar can look through the hurricane and it measures the intensity and the types of precipitation within it. So if you note this light blue material at the top, this is ice. And so the transition of ice to water vapor is something that helps the hurricanes to store energy. And it's something that we did not know before the GPM mission. So after GPM, we have a better understanding of how hurricanes develop and potentially how we can predict their paths more accurately in the future. So again, this light blue material at the top is ice, and we were able to make the connection that this ice is sort of the potential energy and the stored energy for the hurricane. And so as this ice changes to water vapor, that's what powers our hurricane. So if you note beneath all of the light blue sections, there's very high intensities of storm beneath that. So the ability for GPM to cut through and tell us these details about what's going on inside the storm has really helped to shape how we can better sense what's going on in the future. Okay. I said to Mr.
So you see the laser coming from underneath the satellite. So another important mission that was designed and built here at Goddard is the incredible laser of ICESat-2, which is currently mapping the height and location of all the ice in the polar regions of the Earth, as well as glaciers in our mountains and the height of trees in the Amazon. even the health of the coral reefs. So this laser can actually go down about 40 feet in the water to look at the coral reefs. We know our planet is changing faster each time we measure it. And ISAT-2, as well as our other satellites, will help us get ready for rising oceans, more extreme weather, droughts, and changes in the atmosphere. So the satellite has a single green laser, which is split into 6 beams as it leaves the bottom of the spacecraft. We then start the stopwatch to time how long it takes for that laser beam to reflect off the Earth's surface back to the spacecraft, down to a billionth of a second. We can measure the thickness of the ice down to the width of a number 2 pencil. The laser sends 10,000 pulses each second, each pulse sending 300 trillion bright green laser photons to the ground, yet only a dozen will make it back to the spacecraft. We take measurements every 2.3 feet along the satellite's ground power. The reason the astronomers use a green laser rather than a red laser is that it's brighter and the visibility range is longer. So with so many observations coming from our satellite fleet, it takes one of the most powerful computers in the world to keep track of it all. We intake over 1 million pieces of data each hour and feed the information to a computer that puts it all together, allowing us to create complex computer models to help scientists better understand the Earth's climate, of how the Earth works, from our atmosphere to ocean currents to changes on the land. These models help us understand how the Earth works as a system. Everything's connected. What you're seeing in the model is what you're seeing is a model that produces a global numerical weather forecast on a routine basis. Goddard Space Flight Center is the home of the state-of-the-art supercomputing facility called the NASA Center for Climate Simulation. Goddard's high-powered supercomputer is a 15,000 processor supercomputer capable of performing a staggering 160 trillion or more calculations per second.
I saw one of the questions in the chat. So we do have additional testing for satellites. So similar to the temperature testing of satellites, is there any testing for different magnetic field strengths or cosmic ray exposure expected in the space environment? Yes, so those are like the 3 main tests that we do, but we do additional testing for sound. We do the magnetic field strength, and I don't know, Mr. DJ, do you know if we do anything for radiation exposure for potentially for satellites?
We do, yes. We do radiation testing as well.
Yeah. So there's loads of different apps. Those are just the 3 main kind of that we focus on. Sorry, not focus on, the biggest ones I can show you. But yeah, we definitely do a lot more. Okay, all right. So then this is a specific example, if I needed to click, of the type of observations that we're doing. And so the type of models that we're making from those observations. So this one in particular is used to study particles in the atmosphere during the bushfires in Australia that were happening at the end of 2019 and the start of 2020. So if you see the date and timestamp at the top, you'll see end of 2019 and the start of 2020. So what we can do is we can run these observations backwards and forwards and study all aspects of the event and hopefully better understand how it happened and possibly how to better respond to similar events in the future. So those of you who are doing GIS are very much aware of the models that we can create and how you can predict and get an idea of what's going to happen. And then so we can create these models then that are showing us what happened in the past. So hopefully it can help us to make decisions as we move forward into the future. So you can see the key at the bottom is showing you all the aerosols or the particles that are in our atmosphere. Particularly this one's looking at carbon, sulfate, dust, sea salt, and nitrate. So we can see the fire and we can see the carbon coming off of the fire. We can see how it's changing and moving through the atmosphere. And then also how it's changing and moving along the continent of Australia itself as well. So we can see the path that air is flowing and that it's moving. Another interesting thing about this map, aside from what we can learn for fire prevention, is there's also a connection between the Saharan desert and the Australian goodness, and the Amazon rainforest, excuse me. So we have done some studies and sort of made a connection that the Saharan desert, the dust is coming off of this desert, and it, as you can tell, it's flying through the atmosphere to North America, Europe, Asia, everywhere, all over the place. But particularly when it comes down to South America, it's landing into the rainforest, and they believe that it's acting as sort of a part of a fertilizer to help support the rainforest. So I think it's kind of cool to see the connection between 2 vastly different environments. All right, so now we're going to talk about some of our planetary science missions. The first one is our Lunar Reconnaissance Orbiter. So we are sending humans back to the moon. In 2025, we have our Artemis mission coming up. We're gonna have the first women going to the moon, first persons of color going to the moon, and we're super excited. We're really, really excited for this new opportunity to explore technology, explore the moon, and then also to explore the ability to live, I guess, off of Earth. And then we'll use some of that technology and information we figure out to help us as we go forward to hopefully send humans to Mars. So Mr. DJ, would you like to tell us about this mission?
Sure. So LRO was launched on June 18, 2009, and it's still working to this day. And its goal was mostly to create like a high resolution 3D map of the moon's surface, because the last time we went to the moon was in the 60s and 70s, and we have good photographs of the moon's surface. And we also want to look for things like prospect for resources like water, and we want to measure radiation environment. So the LRO is carrying a human tissue equivalent plastic that will measure the radiation that's hitting the moon's surface to see, to make sure it's safe for the humans to go back to the moon. So we're going to go to the South Pole. So part of the LRO mission was to send an L-cross satellite that was launched with the LRO to impact the moon following a spent fuel tank that impacted first. The debris plume that was thrown up by the empty fuel tank was studied by the L-cross satellite before it too crashed the moon and proved that there was water on the moon. So when you're looking at the South Pole, so these are permanent shadow craters where comets, and I'm just reading an article right now that scientists have determined that the ice that you see in there was delivered by comets. This is water ice. You can split the water ice into separate components: water, oxygen, and hydrogen. Oxygen can be used for breathing, and hydrogen can be used as rocket fuel. So we also want to look for other minerals that we can mine for. And we're going to go to the Astrocus Plateau, which you should see coming up. You look at the highlighted rectangular areas shortly, right there. So the Astrocus Plateau contains an abundance of a lunar ilmenite, that's ILMENITE, which is a mineral that contains oxygen, iron, and titanium. So the mineral again could be used for making air to breathe and also rocket fuel. So LRO is looking for resources like that we could probably use when we send up moon bases. So we're going to go to the Taurus Latrobe. So this is the area where Apollo 17, the last mission to the moon, landed in 72. So I just really want to show you how good the resolution of these images are. I mean, from a height from about, it's probably actually got low to about 14 miles one time, the orbit of the LRO. But we could actually see the landing sites of the Apollo missions. There you see the lander that brought the astronauts to the moon, Apollo 17. You can see the tracks made by the rovers that they used to go far away from the lander to look at minerals on the moon surface. There's a rover over there. So we really got really detailed maps of the moon from the LRO mission. So we can use that for when we navigate and do land in the South Pole of the moon. And this is coming in 2025.
So one of the reasons we're so fascinated with the moon is that its surface really hasn't changed for billions of years. And it really is a record of everything that's happened in our solar system. So asteroids, which you can see in this video here, this is an asteroid named asteroid named Bennu, BENNU, and this was taken by OSIRIS-REx, the satellite that went over there to explore it. So yeah, so asteroids are another type of small body in space that are even more ancient than our moon and are remnants of the building blocks of our planets. So we're looking at our moon to help us learn more about the record of what's happened in our solar system. And we're looking at asteroids to help us understand the building blocks of our planets. So here at Goddard, we are leading a mission to return a pristine, unaltered sample of what conditions were like over 4 billion years ago. So in October of 2020, OSIRIS-REx flew alongside the asteroid Bennu, and it took a sample, and we're eagerly awaiting its return, and it should be arriving in 2023. So I will show you, so it's our artist rendition of OSIRIS-REx approaching Bennu. So as you can see from this video here, as you can see, it's very rocky, very bouldery, very craggy, so to speak. But our initial anticipation, as you can see from this artist rendition, is that it was much more beach-like and much more smooth. And so that was something that we definitely learned about Bennu once we got there. So if we had to think about where we were going to approach it and stop to take the sample, basically. So what The way it worked is the OSIRIS-REx came down towards the surface. This arm is about 9 feet or so long. At the end of it is our sample acquisition filter at the base. And so what it did is it came down to the surface. It briefly touched on the surface. As it touched, it blew out nitrogen gas to stir up the regolith, or the soil, so to speak, on the top of the asteroid, stirred it all up, and then it gathered up as much as it could. It pulled it, sucked it into the component right here. And then as it did that, it backed away as quick as possible, so as to not have any of the other regolith get in amongst the instruments for the satellite. Once it was at a safe distance, the arm folded up, and the sample was then put into our sample return pod here on the top. And so this pod is what's on its way back to Earth now. Okay, so one of the main reasons that we want to know what the ancient solar system was like is to piece together the story of the conditions that allowed life to arise. So we're looking at our moon to know what happened in our solar system. We're looking at asteroids to know about the building blocks of our planets. And in general, we're looking at what all of this was like so that we can figure out the conditions that allowed life to arise. So this is our Dragonfly mission, and we're really excited for this one. It should be arriving at Titan in 2034, and it should be launching probably in 2026 or so. So Goddard is involved in many explorations to find life-friendly environments, from Mars and to the moons of outer planets like Jupiter and Saturn. And it really may surprise you that some of the best chances for life are in the outer solar system, on moons that have oceans protected by shells of ice, or places like Saturn's moon Titan. And so Titan has a thick atmosphere that may be similar to that of ancient Earth. So we're very interested in exploring that and to see what that might mean for the conditions that allowed life to arise. So Dragonfly is very unique in that it will be going to Titan. So we're going to a moon that's potentially similar to ancient Earth. And unlike other crafts that we have sent to other places, this is a more like a drone, if you will. So we've sent many rovers to Mars, but a rover is very, tied to where it's landed, and it has to rely on the wheels, and it can only go to a certain amount of distance in a certain amount of places. But with a drone, we're able to fly it around the whole of Titan to kind of take measurements throughout the whole space, which is really unique and really cool. So it has 8 rotors, so it's an octocopter, if you will. So there's 4 on each side. There's 1, 2, 3, 4, and then there's 4 on the other side as well. So it will fly all over Titan, and it has a whole suite of science instruments on board from different spectrometers that will ID the chemical components and look at patterns and functionalities in the molecules that are present on Titan. And then we'll also be looking at surface composition, and then we have a suite of geophysical and meteorological sensors as well. And so we'll be looking at what's going on under the surface, see if there's any moonquakes, and then also paying attention to what's going on in the atmosphere and the air there. So we're very excited, and hopefully this will tell us a whole lot of information about what's going on. So we're going to talk about 2 of our missions from heliophysics. The first one is our Solar Dynamics Observatory.
So Goddard leads many missions to monitor the activity of the sun and track the material it throws out into the solar system. For the last 12 years, the Solar Dynamics Observatory has returned continuous ultra-high resolution images of the sun. High-speed cameras in SDO take rapid-fire snapshots of solar flares and other magnetic activity. We can see images of the full disk of the sun from its deep interior to the outermost layers of the atmosphere. We take pictures every 10 seconds, 24 hours a day, with 10 times better resolution than high-definition TV. These images are taken in ultraviolet and X-ray light, which is invisible to our eyes, but picks out the most active, hottest regions of the sun. SDO will also study the amount of energy the sun puts off in the extreme ultraviolet wavelengths. These are very short wavelengths that get absorbed very high up in our Earth's atmosphere, causes the Earth's atmosphere to heat up and expand, and causes satellites to fall out of their orbits. And this happened in March 23rd, 2001, when the Mir Russian space station entered the Earth's atmosphere on that day and was destroyed. So SDO was sent down 1.4 terabytes of data per day. That's equivalent to downloading 500,000 songs every day. The magnetic field is also looked at. We know this is important because we've never understood the direction of the magnetic field before, and that's part of our research, is to find out what's happening to the magnetic field. And by knowing its direction, that gives us another piece of information to understand where it comes from and how it gets converted into solar activity. The instruments on the SDO are designed to work together. One of the instruments measures the magnetic field, the other one measures what the magnetic field does, and the last one sees how it affects the Earth. So we're going to go to the Parker Solar Probe. So this is the most recent solar mission. This was launched on August 12, 2018. So this is a seven-year mission that will bring the Parker Probe within 4 million miles of the sun's surface. The main objective of the Parker Solar Probe is to learn more about the solar wind, a mixture of plasma, magnetic forces, and particles. The solar wind also travels at immense speeds. It leaves the sun at 500 miles a second. What is the source of the wind? The solar wind is processed by the time it reaches the Earth. By studying much closer to the sun, the Parker Probe will be able to tell us such things as what part of the sun is providing the energy source for the wind particles, and how can they accelerate to incredible high speeds. At its top speed, the solar probe will be orbiting the sun at a speed of 430,000 miles an hour. That's like going from Washington to Philadelphia in under a second. It will also absorb temperatures of 2,500 degrees Fahrenheit. Parker is protected by a heat shield. And if you can look at it right in the front, it's that shield. It's a 4.5-inch carbon foam with a carbon plate on the top and another carbon plate below the shield. The rest of the spacecraft is protected by the shield and will experience temperatures of only 84 degrees Fahrenheit. The instruments will make maps of all the different particles and what energies they're moving at and what type of particles they are. So we're mostly measuring with this spacecraft the bulk of the solar wind and solar atmosphere.
All right, so now we're going to talk about 3 of our astrophysics missions. So all 3 of these do overlap in their exploration of exoplanets and trying to see what is going on, either identifying them or seeing if there's possibly signs of life for those as well.
So this is TESS. This was launched on April 18, 2018. It's the newest exoplanet explorer that's surveying 200,000 nearby bright stars within 300 light years in search for exoplanets. So light is the distance light travels in 1 year, and the light travels at a speed of 186,000 miles a second. So 1 year travels 6 trillion miles. To date, NASA has confirmed the discovery of 5,000 exoplanets. TESS will have 4 large cameras, and each camera has a 16 megapixel sensor that are arranged in a vertical strip of the sky called the observational sector. TESS sees each observational sector for 27 days before rotating to the next one. TESS will use a transit method to find planets, looking for a slight dip in brightness as a planet passes in front of its star. The amount of the dip and the length of time it takes to complete tells us how big the planet is and what the orbit is. The TESS has to see 3 of the same tiny dips of light to be considered as a planetary candidate. During 2 surveys, TESS has looked for signs of planets ranging in size from Earth to Jupiter-sized planets.
All right, so now we're moving from TESS to the James Webb Space Telescope. So this just launched on December 25th. We're incredibly excited to have it out there. It has reached its location, which is the L2 Lagrange 2 point that is about 1 million miles away from Earth. And we have deployed everything now, and now we're working on calibrating our mirrors and getting everything ready to go. So hopefully this April, we should have some of our first science mission images coming back from this mission. So we're beyond excited for that. So so we are all familiar, I guess, to kind of, I jumped ahead, I got super excited. So let's kind of come back a little bit. So we are all familiar with the Hubble Space Telescope and the amazing science that it's doing and it has done. And so at Goddard, we are working on Hubble's cousin, and I like to call it Hubble's big bad cousin, the James Webb Space Telescope. So this was designed, built, and tested here at Goddard, and it's our next big space observatory. So its mirror is about 3 times wider than that of Hubble, and the Webb telescope will have the power to detect water, organics, oxygen, and possibly even signs of life in the atmospheres of exoplanets. And it will also have the power to observe stars and galaxies so far away that their light has taken over 12 billion years to reach us. So this will give us a glimpse of how the first structures in our universe formed and how the first stars began to shine. And we're going to accomplish this using infrared light to observe rather than just regular visible light. So we're incredibly excited and so glad to have that going, and can't wait to see the science that comes back from it. All right, so the Nancy Grace Roman Space Telescope. I'm going to talk about this before I show you the video because it's my favorite video. It's very short and it's very to the point, but the music's great and the words are great, and whoever made it needs it. Like, it's great. I think I've said it's great like 5 times. So anyway, so we are getting ready to build the Nancy Grace Roman Space Telescope here at Goddard, and it will continue our work to explore exoplanets, just as Tess and the James Webb Space Telescope are going to do. And it will also explore a newly discovered phenomenon called dark energy. And it'll do this by looking out into the deep universe. So dark energy appears to be driving our universe not only to expand, but to accelerate in that expansion. So we're very excited to see, I mean, we're excited for every mission, but we're also extremely excited for this one because, you know, it potentially may change everything we know about the origin and the ultimate fate of our universe. So it's going to tell us a lot, hopefully. And this was named for the first director of astrophysics at NASA in the 1960s. Her name was Nancy Grace Roman, and she helped to lead the efforts for space-based observatories like Hubble. So it just seems appropriate to name this after such a momentous woman. All right, so I'm going to play this for you. And if you don't think it's as great and amazing as I do, just pretend. That's good. So again, it's very short and to the point, but I don't know, I think it's really great for sort of like, oh, thank you for letting for like, you know, getting feelings out of me and getting excited and super pumped for it. Okay, so that was the last mission we were going to tell you guys about and talk to you about. So again, we looked at just a couple of our missions within each of these areas. So this graphic is from a couple of years ago, but even from that, you can tell that there's so many missions going on and so many amazing things happening. So each one of these names that you see along here is a mission that's coming up, and we've had, you know, some come new since this point as well. So we're beyond excited and ready to see what's going to happen next and what the next generation of scientists and engineers are going to come up with and what they're going to discover. And then also just to see what our current generation of scientists and engineers are also going to continue to work out and to make happen. So all right, so we would love if you guys have any questions, if you would like to ask any questions. We are your captive audience. I think we grabbed a few of them from the chat, but yes, I see that the comment. So as a former South Florida resident, you experienced numerous hurricanes. You never would have thought that ice was in hurricane. Exactly. Yeah, I'm also from Florida, and so that sort of confused me. I was like, really? What? But I guess from, you know, the elevation and the height of the storm and just the composition of the storm itself, yeah, we have ice on there, and just it's not fair because Florida, yeah, we don't get snow, but then the ice brings us hurricanes. Okay. Oh, nice. You're down the road from White Sands. I have not been there yet. I would love to go visit the facility.
So White Sands is a tracking facility, and also LRO. It sends its images down to White Sands because we do have the Deep Space Network in California, but it's overburdened. So we had to build a separate tracking station, White Sands, for LRO images. And also SDO, so Dynamic Service who uses White Sands for sending up telemetry and also receiving images.
And yeah, so do we offer virtual internships? Currently, yes. I do think that moving forward in the coming years, that I do believe they'll still offer virtual internships. I know we're gonna, like, we offer virtual programming now, and that's something that we didn't do before. And the amount of people that we've been able to connect with and reach out to has been fantastic and amazing. And just having the virtual option, I think, has allowed for a lot of folks, particularly in our internships, that can't come on center or can't, you know, move to a certain site each summer. It allows them opportunity of participating as well. So I hope so. I don't want to make promises for them, but I believe so. Oh, nice. your high school best friend's father was a photographer for space. Fantastic. That's so cool. DJ, you like to do photos as well.
Yeah.
Oh, so we have a hand. Caitlin.
Hi. Thank you so much. My background's in astronomy, and this was just such a giddy presentation. I loved hearing about it. Thank you so much for presenting them. I did have a question on how NASA determines what missions go to what center. So how is something controlled by Goddard versus JPL or some other NASA facility? How do they make that call?
That's a good question. I know we just finished a decadal study with the national NSF, and they're the ones who will pick out which missions. So we submissions, Goddard and all the centers submit missions that they want to do, and all that gets sent to for the decadal study to National Science Foundation, and they will decide which missions we're going with. So all the centers, have ideas as to what they want to do, and they send what they want to do to the NSF, and then when they do their decadal study, they will pick out which missions each census would be doing. Yeah, pretty much that's it. And then we've got 2 missions going towards the sun that were just announced yesterday. We've got a mission going to Venus that got us involved with. And I think there's some other science missions that we're also involved with as well.
So I saw in the question in the chat, someone's wondering if there's any resource links for the James Webb Space Telescope. And so I just put a link to the blog in there as well. So they will put any updates for what's going on in that blog. And then I guess what Mr. DJ asked the next question. One of my favorite websites, it's on my work, I'm on my personal computer. When I'm on my work laptop, if I can find it really quick, I'll put it into the chat as well. So it's a really good website. I'll mute myself so you can't hear me typing. DJ, are there any resources for JWST that you think we should share?
JWST.nasa.gov. Also the Space Telescope Science Institute. They're the ones who actually fly the James Webb Telescope, and I'm going to find the website for that. Space Telescope Science, STSCI. So that website is www.stsci.edu, education. Space Telescope Science Institute. That's the initials.
I just shared jwsc.nasa.gov, and I love this website. So it showed you the countdown, there's news, events, things you need to know. But I like the Where is Web option that you could click on the bottom, because it shows you so you can see, I'm pointing at the computer, sorry, from Earth to the L2 point, but it shows you exactly where it is sort of in the plan. So they're working on the segment alignment here, and you can see the course phasing, fine phasing, the telescope alignment, and the correction. And so it kind of gives you an update of where everything is. And then it also tells you the temperatures on each side too, which I think are really cool. And you can switch English to metric. It's just, I think it's a fun website for like fangirling out a little bit for me, for my personal fangirl. But yes, that's a great website.
Okay, awesome. Thank you guys so much. Did we have any other questions? We have one more. How many ways to say amazing and absolutely awesome?
Thank you. Thank you.
Awesome. Yeah. Well, thank you so much for being here with us today. This was an incredible field trip, and I'm more in the IT field, so this is way outside my comfort zone, but I loved every second of it. So I appreciate it. Also wanted to thank Dr. Millman for being here. She's our faculty advisor for students for the exploration of development of space and an astronomy professor at APUS. So thank you so much. Yeah, on behalf of us and everybody else, unless anybody has any lasting questions.
Well, thank you so much for inviting us to join you guys today.
Yeah, no problem. Thank you again. All right.
Thank you.
Yeah, thank you.
Okay, well, thank you so much.
Thank you.
Have a great day, everyone.
Have a good one. Thank you. Bye.
Bye.
I'd like to ask a question real quick. Isn't there a form that I can fill out to put toward chapter points for the STEM chapter?
You won't fill that out. That's only the leadership team for the organizations. Yeah.
Oh, okay. I thought if I attended it,
No. It's only for the organizations themselves. We record our points for hosting meetings and things like that.
Oh, okay. You know, I was a secretary in another, so I get confused sometimes on that. Okay. All right. Well, thank you. And it was fantastic. This was called a virtual
field
tour.
Trip. Yep.
Right. Or yeah, field trip. Yeah. So cool. So cool. I was wondering how you were going to pull it off. I've never actually been aware if I've been to one, but yeah. And I will look into the suggestion from Dr. Drexler, I think, said something about I should look into
a course for by Dr.
astronomy.
Mm-hmm. Yep.
Okay. I'll look into it, but that might be as far as it goes until I can afford to do something. What is the wSTEM website? Somebody's asking.
I will post it. We are currently in the process of re-upping our domain.